So this glass door problem, I forgot the name of the company, but it's obviously a made up company and it's a made up problem. Because they put a plot to it, like a story behind it and all. So if you're reading it, you're trying to pull out the variables to it. It's kind of hard to do that. So actually, I have a problem that I'm going to work with you today, and I gave you. I'm going to give you a little table, and I'll tell you where that table came from. But let's say like they got there, and so this is the example that they had in the book. I felt like I went through it really fast because I had the prepared notes for you. They're in your folders if you want to pull up the PowerPoint and actually look at it. But the hard part, really, what you missed when you see everything kind of curated the way I did it in class, is that you can't really see what I went through to get there. So I'm trying to go and track what I'm doing. And so I'll give you that handout in a second. But let's say I got to the point where I had these decision variables. Jacob, can you close the door? Put the time element when you're labeling your decision variables. That's not just because it's being required and there's a rubric. It actually makes a difference. And the problem that I gave you today, it makes a difference because they talk about something per minutes and then there's hours. So you have to weed through all that stuff. And if this thing is per week, you have to have everything match up per week. So make sure you put the time element in it. So Y is going to be the same thing, number of windows to be produced per week. These are called decision variables. And the way I like to think of them, I like to think of them as sliders. I can slide these amounts around. I can choose, that's the thing I can choose. I can choose what combination of these two variables I'm going to have to need to get something to happen. And I'm literally going to show you something with sliders today. I just made it yesterday so you can see it. Constraints, when you pull it out of the text, you're really looking at restrictions on what you can do. So they say something like, I can only make 4 doors per week. Well, that's a total. So anytime there's a total amount, it's probably a constraint. And the Zildjian thing that I made this up, pulled it from the numbers from the book, but there is never that cheap of a symbol, is there? Yeah, like I looked at this. I have like things I want that I'm holding off on. I want the K series Zildjian symbols. I'm going to hold off because they're really expensive. But this is a made up problem. So they're in my fantasy world, they're only $32. That does never happen. But if you look at it, the first number you see is 5,000 in that problem. That's a total. Like that's a total amount of material. So that's probably going to be involved in your constraint. That's how you kind of look at your data and that's given to you, like pull out those numbers and then ask yourself what's that number associated with. So the constraints here, if you actually went through the book and read it, is we have like a constraint on the total number of doors that can be made. And they say that. They say total number of doors that can be made per week, blah, blah, blah. So that's the 4. And then they have something like this. Total number of windows, they can make 2 windows per week. And then the total number is constrained by 12. They don't say constrained. They say the total number the plant can make is blah, blah, blah. But you have to kind of pull at the total numbers have something to do with constraints. And then you typically have to ask yourself about non-negativity. Yeah, I can't have negative numbers of doors and windows. So you'll have to look at it and actually remember that. And then they talk about profits. And profits is more like your basic algebra. I don't know when they're teaching this now, 6th grade, 5th grade. They're teaching it earlier and earlier. But, you know, those problems where you have nickels and dimes and they total up to be this. Remember those problems? That's more like your classic put together the algebra equation. That all you had to do to get here because you had to take SATs and they probably had stuff like that. All right. So let's say you got this far. So this is called the objective function. They typically say it somewhere in the problem. These are made up problems. So they're not like real where people have no idea what they're going to ask you and then you have to figure out what they're trying to ask you. They literally say at the end of this somewhere they want to maximize profits, or maybe they tell you at the beginning of the story. I don't remember. It was a long story. Has anybody looked at the book on that? Did you guys have check on reading yet for that? The Window Glass Company.
Yeah, I know it was 5.3.
All right, yeah. So it's coming. So they have a story. You'll see. It's like a novel. There's a story to it. Like, oh, this guy wants to maximize his profits, wants to sell windows and doors, and then they tell you some of the analytic team comes in. They drank some Pepsi. They had a conversation. Like, there's a whole story to it.
I'm pretty sure it's very similar to the one that we did on Friday.
Yes, absolutely.
8-foot glass door.
I did that exactly. But the hard part that I didn't show you is you had to read the story to kind of get to like what's important in this and weed it out. So they're trying to make it as real life as possible. That's why there is a story, but you're still condensing it to a check on reading with a quiz and everything. So it's not really real. It's still kind of Law and Order 2-hour special. All right. So let's say I got all this. How do I solve it? And I'm going ahead. I'm just showing you where it's going so that you know where it's going, so that it makes sense what you're doing today in class and everything. So they're going to show you this plotting the feasible region. And I feel like that's where Cooper wanted to go. He wanted to go and like, I have all these inequalities. I want to solve these inequalities. I did that SAT kind of stuff. I've done it before. But that's not quite right because you don't get an F. What's going to happen is you're going to draw this region, and they're going to call this solving by a graphical method, but it's really just, even in Excel, they're just simulating that same thing that you're doing here. So if you graph it, do you remember like this would be y equals 0? Let me list up my constraints. So the constraints make the feasible region. Got y less than or equal to 6. That's this thing. Because Cooper wanted just to slash the 2's from both sides, right? So that's what you get. And then I did this. I did this in my head, so check my work. Oh yeah, they had one more thing up here. Plant 3. Each plant had constraints, and plant 3 had this constraint that if they can only make 3 doors. Or they had something about the constraint on time. I can't remember where I got this equation, but they had total number of hours that they worked per week at plant 3, and it was a mixture.
3 hours per door and 2 hours per week.
Yeah, so it's like one of those algebra equations. Yeah, so so the total tells you that you're going to have a constraint equation that has something to do with this, and they're not equations, they're inequalities. So that one, if you look at it, I wrote it as y equals mx plus b. Because I know where this is going. That's what you guys asked me for. Where's this going? So let me tell you where it's going. So what you do is you plot all of this, and then you have x greater or equals 0 and y greater or equals 0 as well. These are 2 constraints. So here's x greater than 0, y greater than 0. That right there. That means I'm in the first quadrant. So all my pictures should be here. And then x less or equals 4. 1, 2, 3, 4. This is x equals 4 right here. So it's got to be to this side. And then y less than or equals 6. I should have gone by 2's. Then we can do that. 2, 4, 6. Okay, so y equals 6 is right here. That thing. And you have to be lower than that. So now you're in this box. And then finally, if you graph that, it's a line. And I just did something like, I just picked 2 points. This is 2 and 6. Because if I plop in a 2 here, I get 9 minus 3, which is 6. So that gives me the y value 6. And then, and I put 4, 3. somewhere here, and then this is the line. This is y is equal to minus 3/2 x plus 9. And then it's got to be lower, the y values have to be lower than that line, so it's got to be here. So if I shade the region that's bounded by all of these three, it's going to be that region there. In this case, x's are above or below 4, y's are below 6, y's are below the line minus 3/2 x plus 9, and yeah, so I got it all. And then I also x is bigger than 0, y equals bigger than 0, puts me right here. So this is called the feasible region. That's the name of that. Right?
How did you get 3x plus 2y?
Oh yeah,
How did you get that?
yeah, sure. I just did this like that, subtracted the 3 from both sides. Oh, wait.
Wait, where did you get that?
Yeah, so this equation,
Yeah.
the other day, remember I showed you like this long drawn out story that came from the problem, right? So I'm continuing the story. I'm trying to squish it into a longer episode. So that's where that came from. So all that stuff has to be built. Today, I'm going to give you a chance to try it yourself. What do they call that for cadets? A developmental opportunity to try it out yourself. So there you have the words and the story. I put some Oompa Loompas in there. So I tried to make it a story. All right, so that's called the feasible region. And that means that over this feasible region, you're looking for the maximum profit. So that means all the x's and y's that you plug into this thing up there have to give you, they're going to give you different profits. So if I start like this point here, 0, 0, and I plug it in there, I'm going to get profits is equal to 0, which is not good, right? X, Y, P. So I can start looking at this. So if I put 0, 0 in here, that's in the feasible region. That's in that shaded area. So I get 0. That's not good. Give me another one that you want to pick a point from the feasible region. 2 and 4. So if I plug 2 in there, I get 600. Plug 4 in there. What do I get for total here? Louder. I'm bad at arithmetic. What? I think it's big.
First time in 2000? Yeah, 2000. Yeah, 2000.
Okay, are you sure?
Yeah.
All right, so that's bigger. That's a better profit, this combination. So you can just check out some combinations and see what's going to give you. But you have to pick your x's and y's in the shaded area when you do that. Right? 2 times 600 plus, is it 3,600?
No.
No, 2.
It's 2,600.
Okay, I trust you. I had actually, after I left West Point, I taught at Jersey City, and I had to teach a remedial course on arithmetic. And I don't think the students trusted me. It was really hard to do arithmetic without a calculator. But I did arithmetic, I can tell you that.
So I think 2 6 is probably the best of all.
You think so? We'll see. So here's the thing. So here I have an x and a y, and you used to like pick x's and put it in a function and plot the y and xy on the xy coordinate. You could do the same thing with 3 dimensions. So I'm going to show you a picture in 3 dimensions so you see it. So if you think about what's going on, like if you pick an x and a y, like 0, 0, and I plug it in there, I get 0. So that's on, I can think of 0, 0 being on the floor, and then up here, the y didn't go anywhere, right? The elevator just stayed at 0. But the elevator at 2, 4, which is on the x-axis, you'd go 2 and over 4, and then you plot, it's 2,600. So you get a different number for every x and y on the floor, where this is like, think of this as a rug on the floor in this shape. There's a height for every place you were on the rug. Does that make sense? The height would be the profit, right? So can you imagine that? Like, does it make sense what I'm saying? You don't have to like be able to do this. I just had it graphically map it so you can see it. What do you think you're going to get if you plot these points in that kind of a thing? You're going to get something curvy. What's a three-dimensional version of a line? It kind of looks like a line because it doesn't have any squares in it or anything. You're going to get something like a trapezoid. You're going to get something like a flat top and leaning one way or the other. It's got its own slope and everything. It's like we call it a plane. So it's like a piece of paper over the rug. That's going to give you profits, right? So I'm going to show you what that looks like.